Hello and welcome to the Cambridge Technical Revision Sessions for Unit 3 Principles of Mechanical Engineering, and we're going to be looking at calculating the centroid of a laminar or two-dimensional object. I've got here as an example a piece of aluminium, it's a few millimetres thick, and it's been calculated and drilled at its centroid to basically find its centre of its mass. And we'll show you how that can actually balance. That's a little bit of an IKEA backdrop, some posters that I've got, just remind me of some basic mathematical principles. So here's a piece of aluminium and it's been drilled in our centre. And if I place that on there, it should balanced around its centre quite nicely. Now this principle is really important, and being able to find the centre of gravity and mass of an object, it's something that is important to NASA. So there's a NASA sheet explaining the centre of gravity on the computer there. And what we're going to do, you have to let me reset my camera now, is we're going to show you how to do calculations on centroid of an object. Now this example for a design for a scale rocket, so these are the actual measurements we're going to use, 15 by 15 by 15 millimetres, and the whole thing is 90, just under 100 millimetres tall. The exam questions will always give you a starting point from which you are to calculate your coordinates, so you need to be aware of that. It's a very important part of the exam question. Now this is an overcomplication, but the idea is to show you the different separate elements of calculating the different components and then how you average them out to find a centre point. We're going to work on the y-axis only. With a symmetrical object, the coordinates, as you'll see in a minute, are, because it's symmetrical, quite predictable. So the centre of gravity is going to act down the centre of this object. So the coordinate from A for the x bar, if you will, for the whole object is going to be this centre line. So 15 and half, 15, 7.5. So our x bar coordinate will end up being 22.5. So if you see that in the exam question, you can work that out quite quickly, and then you can focus on calculating. In our case, we need to find the height of the centre of gravity point, so we're going to be looking at the y bar. Before we do that then, I want to just look at some simple shapes and how the shapes work separately, and then we're going to work out how they add up together. So the most obvious shapes that you're likely to encounter are squares and rectangles. And these, as you probably imagine, aren't particularly complicated. The centre is going to be quite easy to find, and it's basically going to be half of the base or half of the height. So another way of writing that would be B2 or H2, like that. So calculating from a given position for a rectangle, basically it's going to be half the distance and half the distance. For a right angle triangle, and you will only be asked three basic shapes, you're going to be asked right angle triangles, you're going to be asked rectangles, and you may be asked semicircles. For a right angle triangle then, the x bar distance would be a third of the base, and the y bar would be a third of the height. So, and as we did here with this shape, and just to prove that as a point, And we've seen this balance, and if we look carefully at this, you can see that distance is approximately 37, 38. So if we do 38 divided by 3 equals 12.6. If we check that dimension, you'll see that that is on the centre there. It's at about 13 for that centre point. This distance here is about 103. So you do 103 divided by 3 equals, whoops, 34.3. So if we check that, 34.3, that's more like 35, 36, so a little bit over in that direction, but it doesn't seem to have affected its balance. But that's how you would calculate that for a right angled triangle. It's really important to note though that so for here, for example, the exam question is asking from this corner here, which would be the same as that corner. So that distance would actually be 2/3. So you need to be very specific about where they're asking you where the coordinates are from and how you calculate them in reference to where. So that would be 1/3 in there, and that would be 2/3 in that x direction if it was an x direction question. So be careful of those in the examination. The final shape that you're likely to encounter is a semicircle. Again, semicircle is symmetrical in that direction, so that's going to be 1/2 of the diameter. But this direction, be aware that you could get any of these in any direction you want, so in which case we'd be working it that way. And to find that point, there's a formula that you need to know. It's 4r 3 pi. And you'll be given that on a sheet in the formula booklet. There'll be an example of these for you to look at, and it will give you base divided by 3, and it will give you 4r over 3 pi that you can use as part of your calculations. So that's how I can find the centroids of individual objects, but you won't get that in an examination. You're likely to get a combined object like this, and you'll have to work out the centroid from combining these, or finding the average, mean average of the centroids of these objects from a given component, or from a given coordinate starting point. So the formula we would use for this is typically we have the x bar and the y bar multiplied by the area total would be equal to the sum of the individual x bars and y bars multiplied by the individual areas. We don't need to concern ourselves with the x bar, so we're just going to look for this particular scenario at the y bar, because the x bar is, because it's symmetrical, it's going to be 22.5. So we're looking for y bar multiplied by the area total is equal to the sum of the y bars, that's the y coordinate going vertically for each component, multiplied by its individual areas. So we'll work very quickly. What I like to do is we break it all down into separate components, calculate the separate areas and the components, and then work out the formula. So let's go through that quite quickly then. So we'll start looking at the semicircle. So we've got a position there somewhere that's going to be 4r 3 pi. So let's just work that out up here then. So we've got a radius of, well, that's 15, so the radius here is going to be 7.5 for that. So we're going to have 4 times 7.5 divided by 3 times 3.142. So that's going to give us 30 divided by 9.426, which will give me a y bar, just that distance, not the distance from A, but it will be that distance plus 3.18 millimeters. Okay, so the actual Y bar will be 30, 60 is 90, so we're looking at 93.18. So let's have a little Y bar there, put a C next to it for a semicircle, and then we need the area, which is going to be 7.5 squared times, so let's just make a quick note so I'll find a bit of space somewhere. 7.5 squared times 3.142. We've got half the semicircle, half the circle, so that'll give us 88.4 millimeters squared. So 88.4 millimeters squared. So that's the first sum, if you will. That's going to be the first part of this arrangement here. Let's look at the rectangle. So we've got a rectangle here. Just ignore the little detailing. 60, no, not 60. Look very carefully. This rectangle there, its centre is going to be around here, is 70. There's the 10 there. So from there, that position will be the 20 from here to there. That's going to be 55. So the Y bar will equal 55. And the area is going to be 15 times the 70. It's going to be 1050 millimeters squared. Okay, so we've got our second component there, and now we need our third component, or two third components, which is our two triangles. So let's take one of those, just have a look. We've got 30 by 15. We don't need to work that one out. We know that because they're symmetrical, these two will cancel each other out and will give us an x bar of 22.5, so we just need the Y bar. The Y bar was the height divided by 3, so 30 divided by 3 gives us a Y bar of 10. And the area, 30 by 15, is going to be 450. Half of that is 225 millimeters squared. So we've got our third and fourth component. So just make a little note, times 2. So we get that right. So we now need two things. We need the total area, and then we need the individual areas and the individual Y bars writing out. So let's do that. So we end up with Y bar multiplied by the total area, 15, let's see, 8.4 multiplied by that particular Y bar should give us something equivalent to the sum of, start with our semicircle, and a little notation up there, 93.18 multiplied by 88.4 plus, we've got our rectangle, 55 times 1050 plus, and we've got our triangles twice. I'm going to write them out both. You could just sort of sum them up, but it's 10 times 225. That's going to be plus 10 times 225. One for that way and one for that one. Okay, so that is going to give us, well, let's work these individually out. So we would end up with 8237 plus 57750 plus 2250 plus 2250. So we're going to have a total here of 704 8, 7. And that's got to be equal to something times our 1588. So if we do a little bit of algebra, I'll switch that on, 70487 divided by 1588 is equal to, so our y bar should be 44 point, call it 44.4. So that should be, our x bar we've already done, so the centre of mass, the average of all of these is going to be 44. So 20, that's the scale diagram, so let's just pop a ruler on there, pull that back a bit, so it's going to be there. That point there is the centre of all three of these, 4 of these components. So any force acting on this design will cause the design to rotate around this centre point. Hope you found that useful. I hope you're able to carry on and practice some of these and enjoy a little bit of rocket science. Thank you.